In this video, we're going to look at the multiplication rule and how to compute probabilities using that rule. This first video is going to use events that are independent. Another video will have events that are dependent. In general, when we want to compute the probability of two or more events happening at the same time, like two qualities, like existing in the same person, or if we want to have events happening in sequence, like the first thing happens and the second thing happens and the third thing happens, then that's a good example of using the multiplication rule to find those probabilities. So first, to use this rule, we need to figure out if we have independent events or not. So for example, if you're randomly selecting people, generally those people will be independent from one another. So you can go ahead and use this rule. Are you sampling with replacement? Are you putting back the objects into the bin and pulling out again? Then yes, you can use independence. Or especially if it says the events are independent, go ahead and use this rule. So the multiplication rule for independent events says the probability of A and B both happening is equal to the probability that event A happens multiplied by the probability that event B happens. So notice that word and there. You might also see in some notation, it looks kind of like an A without a little cross there. That's a key to use and as well. Just depends on the notation that the textbook uses. So here's an example from an article that I was reading. It says that in this New York Times article, in America, about 70% of tipped restaurant workers are women. And let's suppose that we randomly select 10 restaurant workers from America. So our question is, compute the probability that they are all women. So we know in general that you could kind of go to a person and they have a 70% chance of being a woman if they work in a restaurant and are tipped. We want to find the probability that we get 10 women. So the first one is a woman, and the second one, and a third, all the way up to the 10th. So that keyword and is telling us multiplication. And also we are randomly selecting the women, so we know we can use independence. So we're trying to find the probability that the first person is a woman and the second is a woman and the third, and I could keep on going all the way until we get the 10th person to be a woman, because that's what the question asks. So we have independent events. We know the probability of any person being a woman who works being tipped at a restaurant. That is 0.7. Well, we also have a second person, and they also have a 70% chance of being a woman. And we keep on going until we have 10, because we want to select 10 people. So in all right here, we have 10 multiplications for the 10 different people. So we can write this in exponential notation, 0.7 raised to the 10th power, and this will give us our probability, which is 0.0282. So in all, there is almost a 3% chance that if we selected 10 women, if we selected 10 restaurant workers, tipped restaurant workers, they would all be women. So a very small chance. Let's flip this around and let's compute the probability that they're all men. Well, the probability that the restaurant worker is women is, let's assume that that's the complement of men. Not getting into too much detail about that, let's just assume that they're opposites. So the probability of woman is 1 minus the probability that the person is a man, or the probability that the person is a man is 1 minus the probability that the person was a woman. So this is the one that we want. I just wrote out the other one just because. So what's the probability that the person's a man? 1 minus 0.7, so we get 0.3. This is the number we want to use. So it's just like before, when we had 10 women, we multiplied 0.7 to the 10th power. Now we have men. So the probability that we have all 10 men is 0.3 raised to the 10th power there. 0.3 to the 10th. So doing this on my calculator, I get 5.9 times 10 to the negative 6th. So this is a good point to pause right here and look at this number. This is a probability. The probability we get 10 men from our selection of 10 restaurant workers. And this is a really small probability, I can tell, because it has a negative 6 exponent. So we move that decimal places 6 to the left. So if I wrote the 5.9 down, I'd move the decimal place 1, 2, 3, 4, 5, 6. So there's my decimal place. Fill in with zeros. All right, so that's a really tiny number. Don't mistake this and say that the probability is 5.9. Some people write that the probability is 5.9, but that does not make sense because probabilities have to be between 0 and 1. We can't have a probability greater than 1. So if you see a 5.9, read all the way to the end of the line at your calculator and then put it back in decimal notation, or it's okay to also leave this as scientific notation. But of course, follow the directions on the problem. So 1, 2, 3, 4, 5, 6. Yep, this looks good. We put 5 zeros in front of that 5 for the negative 6 exponent. If you want to, you could round this as well and put the answer as 0.00001. That would also work. So very small chance because there's a 30% chance of getting 1 man, and if we needed 10 of them, then it keeps decreasing the probability all the way to very small. Our next example, we have 2 independent events, so events that aren't going to affect each other. The chances that a baby has a certain birth defect affecting their heart is 1.5%. The chances of a baby born with an umbilical cord looped once around its neck at birth is estimated to be about 30%. Different studies give different numbers, but we'll just run with 30%. And let's assume that the events are independent of one another. Compute the probability that the baby is born with the birth defect and with 1 loop of the cord around its neck. So there's that and word. We want both qualities to be present in the baby. So if I write out some notation, probability of the birth defect, I'm just call that BD, and that's 1.5% or 0.015. There's the other event, which was the nuchal cord or the umbilical cord around its neck. We'll call that U. P of U is equal to 0.3 or 0.30. If we want both of these together, we want the probability of the birth defect and the umbilical cord. Oops, erase that. We know they're independent events, so we'll multiply the probability of the birth defect times the probability of having that umbilical cord around the neck. So we'll take 0.015, multiply that by 0.3, and we got 0.0045. So the birth defect had a really small probability. The cord around the neck was quite higher, but by the time you multiply them, having both of those is a less than 1% chance. So we could even write this as 0.45% chance. The next example uses the word at least. So these are 2-step problems because we need to use a complement rule and also use a multiplication rule. We're going to use the tipped restaurant workers again, and this time we're going to select 3 workers. It'll make the multiplication go a little bit faster for example 4, and I'll reuse this data. So what's the probability that we select at least 1 woman if we're selecting 3 restaurant workers. So here's the word at least. And what is it? We want at least 1 woman. So I like to draw these out with a number line because it can get a little confusing when we start looking at complements. Here's 0. That's the fewest number of women that we could have in our sample. Then the maximum is 3. Oh, I'm going to identify that we're talking about women here. And then the other options, we could have 1 woman in the group or 2 women in the group. Those are the only options we can't have. We can't have 1.5 women. It's one of these 4. So what do we want? The probability of at least 1 woman. So I'm going to highlight this. This is what we want. In our group of 3 people, we could either have 1 woman, because that is at least 1. We could have 2 women in the group, because 2 is greater than 1, that's at least 1. Or we could have 3 women in the group. That's at least 1. Any of these scenarios would satisfy at least 1 woman. So what's left over? 0 women. So if there's 0 women in the group, what would the group look like? That would be all 3 men. You can go through and look at these other ones as well. If there was 1 woman, you'd have 2 men. If you had 2 women, that would mean 1 man, and then 3 women would mean 0 men. So computing the probability that you get 1 woman, or 2 women, or 3 women, that's a lot more math than this fast way, which uses the complement rule. So the probability that we have at least 1 woman is equal to the complement of all men. So 1 minus the probability of all 3 of the people being men. And this last probability that I just wrote out, all 3 men, since we're randomly selecting people, we get to use our multiplication rule. So the chance of having a man in the group is 30%, and we want 3 men. So we're going to take 1 minus 0.3 to the third. So that's 1 minus 0.027, do the math, and we get 0.973. So the probability of selecting at least 1 woman is about 97%. And this makes sense because the chances of getting 1 woman just randomly selected would be 70%. So to get a combination of at least 1 woman would be pretty high, you'd expect. Now let's redo this question, but we want at least 1 man. So I'm going to draw my number line again. So we could have 0 men or 3 men. And since I want at least 1 man, I circle, this is what I'm interested in computing the probability of. So the thing that I have left out is 0. 0 men means all 3 women. So what's our question again? The probability of at least 1 man. That's the complement. So our complement rule says 1 minus the probability. And I'm going to write this out just a little bit more. 1 minus the probability of 0 men in the group. Well, what does 0 men in the group mean? It means that there's 3 women in the group. I could have written this detail out in the last problem, but I just didn't. All right, so 3 women in the group, that's 1 minus 0.7 raised to the 3rd power. So we have 3 for 3 women, 0.7, because that's the probability of just randomly selecting 1 woman. So that's 1 minus 0.7 to the 3rd is 0.343. Do the subtraction, we get 0.657. So the probability that you select at least 1 man is about 66%. Try using these number lines for when you have to do at least problems, because you can clearly see what you need to include and what you need to exclude. All right, last example we're going to do an at least problem with a tree diagram. So a tree diagram is just another way to visualize using the multiplication rule. And it uses branches and little dots where you have branches branching out from a node. So we are choosing 3. I'm going to write that again. Choose 3 people. So when you're choosing your 3 people, you have to have a starting point. There are 2 options for the first person. The person could be a woman or a man. The chances that you randomly selected one woman just from any person is 0.7, and then man is 0.3. I'm going to extend these a little bit. Now you go to pick your second person. So let's say we came from this starting point. Let's write start. You started, you picked a woman first. Well, now you're going to pick your second person because we need to pick 3. What could happen? Well, you could get a woman again, 0.7 probability, or you could pick a man, 0.3 probability. So as you go from start down to the end of these branches here, you're looking at the ordering of how you picked people. Woman, here's woman, then man. And we keep going out with these branches until we have chosen all of our people. So maybe we chose a man first, then you could pick a woman next, or maybe a second man. 0.7 probability, 0.3. And now we start our third branching. So this kind of area right here was when you picked your first person. This area right here is when you picked your second person. And then this last set is when you pick your third person. You'll notice that the tree diagram gets quite cramped the more people you have to select because you keep having all these branches coming out. So every time I split off, I go back into 2 branches because there were only 2 options, male and female. If we included a third option, then every time you split, you'd have 3 branches, and then this would get really crazy. Now I'm going to fill in all of these options here. So I filled in these 0.7s and 0.3s because they represent what happens at that exact point in time. I'm not looking at the course of everyone selected. It is when you go to choose your third person, what could happen? Woman or man, and then the probability is associated. Now, when we get to the very end here, this is where we're going to look at all together. This is the cumulative. If you look at each end branch and follow backwards, it's going to tell you what order you picked your people. So woman, woman, woman. The chances of that happening would be 0.7 to the third power. Now let's go to the second branch. If I backtrack, it's easier to see all of my options because you don't have to figure out what you already did. You just have to go back to the start. So that was woman, woman, man. Woman, woman, man. So the probability of getting that exact pattern would be 0.7 squared, and then at the very end was your 0.3. Now I'm not doing the multiplication here. I'm kind of running out of room, but you get the idea of what you would do for multiplication. So this third branch here, woman, man, woman. So woman, man, woman happens to be in the same order, frontwards and backwards. 0.7 times 0.3 and then times another 0.7. And then I just keep on going until I have all of these possibilities for the orderings of 3 people. All right, here we go. All the outcomes. So when you have a tree diagram, you have all of these and probabilities. Woman and woman and woman. Woman and woman and man. You just throw in the word and between them all. When you multiply them all together, you have the chances of getting that specific order. So you can go back now and look at some of these outcomes here. So if I said, well, what's the probability of all women? Here is all women, 0.7 to the 3. What if I wanted to find the probability of all men? Well, I just look for MMM. Here's the probability. If I wanted at least one woman, so at least one woman, well, I would look at all of my options and say woman, woman, woman. Yep, that has at least one woman. Woman, woman, man. At least one woman is in that group. And I look through all of my options and find out, just look and see which ones had at least one woman. You can add up all of the probabilities on this right side, and then that would get you the exact same answer as we got up here, 0.973. See how there's lots of options for getting one woman? Is the woman chosen first? Is the woman chosen last? That makes a difference in the total. You'll notice that the numbers are kind of the same. There's 2 0.3s and a 0.7. Here's a 0.7 and two 0.3s. They're just in a different order because they were selected at different times. But they have the same probability because either way there's just one woman in the group. Or we could put the woman in the middle as well. There's the same 0.3, 0.7, 0.3. There's still 2 and 1 of the other. So I could go on talking about this tree diagram, but this is kind of the general idea that you start here at the beginning and then branch out for all of your options. This diagram always had 2 options at each node, but sometimes you lose options. Maybe your tree is stunted and this section didn't happen. Some problems are like that. This one didn't happen to be the case because you could always start over from the beginning. It was like starting fresh every single time you chose a person. So there we go. How to use a tree diagram to use the multiplication rule. We've looked at some at least one problems. We've looked at 2 independent events and found the probability of having both of them occur at the same time. And then the first one, randomly selecting people, where we get to assume that the people are independent from one another.